Hello everybody, welcome back to the Gregorius Maths video. Apologies for the lack of upload yesterday. Yeah, in my defense, I was busy doing maths, so, you know, yeah, not okay, whatever. Anyway, let's not dwell on the past. Let's press on to the future. So, today is day 8, even though it should be day 9 of the Advent calendar. And, yeah, today is a bit of a funny video. It's more of a joke of a video today. Yeah, I was on NLab and I saw their article on trigonometric identities, and I thought it was really funny. So I'm just going to sort of talk about that for a second. Nothing too insightful or deep, but yeah, I just thought it was really fun. So I thought it would make a cute little YouTube video. Anyway, so, okay, a normal person says, okay, a trig identity is, say for example, I'm going to take this example for the whole video. Sine of a plus b, I believe, is equal to sine a cos b plus cos a sine b. I'm pretty sure this is true. If not, you know, whatever. Pretend I said something true. Anyway, we have this trig identity, right? So a normal person, a Wikipedia reader, if you will, would say, okay, this means that if you do sine and you add these two, these could be complex numbers, a and b, and you apply the sine function to a plus b, you get sine a times cos b plus cos a sine b, right? You know, you just get the same number on both sides, right? And I thought that was the end of the story, but it turns out that, you know, NLab have a different explanation for what's happening here. So for NLab, this is actually a commutative diagram. So okay, so what's going on here? So NLab instead considers the category of Cartesian sets. So they consider a category in which we'll call it C, in which the objects of C are just R0, so points, R, the real line, the plane, the, I don't know, X, Y, Z axes, and so on. Just any n copies of the real line, basically, are objects. And the morphisms are partial functions, so wherever they're defined. So for example, tan being sine over cos isn't defined for the whole domain. So they're partial functions composed from rational functions and trig functions. So basically, addition, multiplication, sine, and cos. These are our morphisms, just like the morphisms are generated by this, basically. So there we got rational functions and rational combinations of trig functions as well. So this is the category that we're working with. And in this category, yeah, a trig equality is instead just what is it? It's just a commutative diagram of, so for example, this one, let's think about this. So we want to do sine of a plus b. So, okay, we need a plus b. Let's focus on this side first. So we're starting with R2, and we map to R. So we'll send AB to a plus b. So we'll just add the two elements, and then we'll do our morphism sine, and we end up in the real numbers. And if you compose these two things, you get sine of a plus b. But the other route we could have taken is, instead of doing that, well, what could we have done to get this? Oh yeah, if we could take AB and we could turn it into the pair, so we're going into R2 again, we could turn it into the pair sine A cos B cos A sine B, for example, which is perfectly legal, we can do this. and then again we just send the pair to the sum. And this identity here is just saying that this is a commutative square. So trig identities are really commutative diagrams. Now, why do I bother getting? Why do I bother putting monoidal categories in the thumbnail? Well, the reason I've done that is because further along, if you keep reading the NLab article, you'll see they start talking about something, something, something. This can also be thought of as, or they maybe even say more precisely, this can be thought of as an equality of morphisms in the monoidal category structure induced by this category. So we're not going to go into the whole details of monoidal categories now, but basically it's a category where you have a natural notion of like multiplying your objects. And for example, in the category of sets, it's just Cartesian products. That gives you a monoidal structure on the category of sets. Now, in this category, we have a very natural monoidal structure given by just, again, doing the Cartesian product, because if you do R2 cross R3, you get something isomorphic to R5, for example. So yeah, we'll just call our product, maybe it's imprecise to call it the Cartesian product, but we'll call our monoidal structure Rn, and they usually use the tensor product notation. I'm just going to say times Rm. I'm going to define to be Rn plus m. And this defines a monoidal structure on our category. And so in this case, what do we have? Well, we have an equality of morphisms which stems from, so on this side we have, if we do R times R, if we have a map from R times R, which is just addition, from R times R into R, which is just addition, and then we do sine, that's one morphism that we can get if we just compose these two. But what we could also do is we could start in R times R. We could then, what could we then do? We could then duplicate our elements. So we could then go from R times R into R times R times R times R. And what does this do? This sends AB to the pair AB, AB. Okay. Then we could send this. So now we've got AB, AB. We could then send this to, what could we send this to? We could send this to R times R again. By doing what? Well, we could then just apply sine cos, cos sine. So we're doing the map sine times cos, where by times I mean in the monoidal structure, and then times cos times sine, like this. So we apply this map. Now we have, oh sorry, where are we? We're still in, yeah, we're still in R cross R times R times R, I believe. And then, now we have, what do we have? We have sine A cos B cos A sine B. So then we go back to R. Oh, no, hold on. Let's go to R times R first. So we got sine A cos B cos A sine B. So we'll take each of these and we'll multiply them with each other. So like we'll take the component from here, multiply it, and we'll take the component from here and multiply it. So we're doing multiplication times multiplication. Well, when I say times, I mean in the monoidal structure. And then we have a pair, if you're keeping track of what I'm doing here, we have a pair sine A cos B as one thing, cos A sine B. So then we can finally get back to R via addition. And in this monoidal structure, this trig identity is just saying this morphism from this composition is the same as, is equal to the morphism from this composition. So yeah, there you go. That's trig identities if you learnt maths from NLab. So if you were in secondary school and you learnt this, but your teacher was Professor NLab, or I'd actually, I should know who created NLab, but whoever he is, respect to you. I think it's John Bate. I don't want to guess. Anyway, respect to that guy. But if he was teaching you trig identities, this is what you'd be learning, which is kind of funny. Anyway, yeah, I thought this was amusing. So yes, and I just wanted to make something fun. Apologies for yesterday, but we're back in business, and I'll see you tomorrow, hopefully. Goodbye.